Good afternoon, everybody. My name is Javier Banos. I'm here representing Veeco. I'm with the marketing group in our MOCVD product line. And my topic today is how do we use MOCVD to bring in, to enable high volume manufacturing at lower cost for microLEDs. The outline for today, I'll do a brief introduction. Then I'll describe Veeco's MOCVD product line for microLED epitaxy, and then we'll go into some details about how we tackle costs through the design of our epitaxial systems, before then wrapping up with some conclusions. Okay, so we've talked about this in a few presentations already today. I'm sure we'll continue to hear it, but cost has become or is still a key obstacle to the mass adoption and the development of the microLED industry. I like to show a picture here that comes from our friends at Yole in their last report, in which they always talk about how much cost reduction is necessary over time to really reach the levels of adoption that as an industry we want to see for microLEDs. And there's a number of factors that contribute to it across the entire process flow for fabricating microLEDs, but certainly epitaxial equipment plays a contributing role. Also, we're at the very beginning of that process flow. So through elements like productivity, material quality, defectivity, these are all aspects that can end up adding up and contributing to a starting point of the process that might be already hurting the total cost equation. So we want to make sure that from the very beginning we are playing a part in the reduction of costs, and that's what we'll discuss in the rest of the presentation today. Before I go into a description of our product line, I want to acknowledge the two main approaches to fabricating microLEDs that exist today, and some of these have also already been discussed earlier in the day. The first one is the more traditional approach of making traditional LEDs through GaN on sapphire for blue and green, as well as Allen gap on gallium arsenide for reds. And that is in contrast to what we're seeing more and more of, which is LED directly onto silicon wafers. That's through GaN on silicon for mostly blue LEDs, which would then, through color conversion or some other method, would deliver red and green colors. The traditional approach brings us up in wafer size from 4 to 6 and now more and more 8 inches or 200 millimeters. The second approach, of course, takes us all the way to 300 millimeters. The benefits from the extensive amounts of silicon wafers, as well as equipment for processing those silicon wafers in fabs around the world. They each have advantages and challenges. A significant advantage of this approach number 2 is the direct integration with the CMOS backplane and some kind of simplicity in achieving that integration. But at the same time, there's a lot more experience over time in the industry of making these type of traditional LEDs. But it can be a high cost process, requires multiple mass transfers. So there's pros and cons on each side, and there are many companies working diligently on resolving these challenges, as we know. In terms of applications, we see everything really being applied for traditional LEDs. We're seeing on GaN on silicon for 300 millimeters a lot of micro displays for augmented reality and some non-display applications, and some of them were also described earlier today. So those might end up being big in this approach very specifically. And I wanted to show this before I go on to my next page, where I map the Veeco offerings for each one of those. It's basically what we call our Lumina product family, as well as